Okay, hello again, and this video we're going to be talking about functions. Most of the problems we're going to be talking about here are from a graphing aspect. In other words, from a graphing point of view, we're going to be talking about one-to-one functions. If one is a function, vertical line test, horizontal line test. We're going to be talking about vertical, horizontal shifts, orientations. So I guess this graphs of functions, maybe this might be the best title for it. Graphs of functions. We're going to be talking about different things. First of all, a graph of a function. You can take your calculator and graph just about any function on your calculator. I'm not going to do calculator graphing in these reviews because most of the time that's one of the problems we have with students. They know too much how to use the calculator, and we're not going to do that in here. We are just reviewing the mechanics of the algebra that we're in, and trying to help you remember some of the algebra that you may have forgotten. First of all, any function can be graphed, and we'll start with the vertical line test. If you have a function, and we'll put that function right there, doesn't mean anything, and I take a vertical line and draw a vertical line on this, I'll just color it green. If I draw a vertical line and it only crosses at one spot, it only intersects at one spot, then that means this is a function. That's called the vertical line test. Vertical line test, if it crosses one time, then that means it is a function. So, of course, anything that looks like this would not be a function. An ellipse or a circle. So anything that has some kind of circular or anything that looks like a hyperbolic or a hyperbola, your chances are the vertical line test is going to show you, of course, that all of these cross at different places, and more than once it is not a function. So that's one little quick test you can do to check to see if you have a function or not. A one-to-one function is tested by the horizontal line test. Horizontal line test, if I give you this function and I draw a horizontal line through this function, you can see that it crosses more than once. And if it crosses more than once, it is not a one-to-one function. So if it crosses once, horizontal line test. If it crosses once, then you have a one-to-one function. Anything else, it's not going to work. Now you see that this one does, and of course this one, if you did this one, it wouldn't. But one kind of like, I'll draw this in red, if you had one like this, then you can see that it only crosses once. And therefore you know that's a one-to-one function. Okay? Now I'm going to draw a parent graph for you. I call it parent graphs. That's called the vertical. This is called the vertical line test, horizontal line test. Symmetric, odd or even. Okay. If you have a even function, an even function would be x to the second. It is symmetrical around the y-axis. See? It's symmetrical around the y-axis. The y-axis is the mirror. This is an even function. An even function is symmetrical around the y-axis. The y-axis is like the mirror. Where an odd function is symmetrical around the origin. And that is an odd function. And odd is symmetrical around the origin, meaning that the origin is the mirror. Okay? So those are just some graphical representations of some functions. Vertical line test if it's a function or not. Horizontal line test checks whether it's a one-to-one function. And just an even function is symmetrical around the y-axis, and the odd functions are symmetrical around the origin, even though that's not a real good representation, but you see it's a review, so you should have seen this before. The next slide, I'm going to ask that you take your paper, turn it landscape. In other words, take your paper of your notebook, and I want to draw some lines. And we're going to draw a line all the way across. And we're going to draw lines down like this. And of course, the more boxes you have, the better, but you need to be able to draw graphs inside these. So doesn't have to be perfect. These are called the parent graphs. And of course, leave the back of this page open, because later on you might draw some more on it. In other words, these are your basic models. When you go buy a car, you have a basic model, and it's called it doesn't have anything on it. In other words, it has 4 tires, an engine, and transmission. Doesn't have air conditioning, doesn't have radios, cassette, CD, whatever. Doesn't have heated seats, doesn't have the carpet and the leather seats. It doesn't have all that. It just has an engine, a transmission, and 4 wheels. That's all it has, and a seat and a steering wheel. That's all it has. That's the basic model. Well, the parent graphs are the basic models for the function families. And if you learn these basic models, then you can sketch a graph just based on what the algebraic equation looks like. So let's start with the first one, x to the first power. Anytime you have a function that looks like x to the first power, x plus 4, x minus 3, x plus 2, you're going to have a linear function, meaning a straight line. Now, most of y'all know that because you've been dealing with linear functions for Algebra 1 and Algebra 2 in high school, and you're used to seeing an x function. But the rest of them, some of you may not know. X squared, this is an even function. F of x is equal to x squared. This is called a parabolic function, or a parabola. A parabola is going to it'll have an x squared, it's going to look like this. Any x to the even power, f of x is equal to x to the even power, is going to look like this parabolic shape. The higher the even number goes, the higher the exponent, the more squared the bottom is going to be. And I'd like to mention the ending behavior. Ending behavior on a even function, I don't use red highlighter, sorry. One, you can't see it, and I don't like the red. So let's use green. There we go. When you have an even function, the ending behavior is going to look like this, meaning the arrows are going in the same way. direction. So you need to write down ending behavior. Let's do that in the between the two in red. Ending behavior for both of these is going in that direction. Okay? So the ending behavior is in both in the same direction on an even function. All right, then let's talk about the odd functions. The most basic odd function is your x to the third power. And that's going to look like this. And x to the odd, the higher the exponent, the more flattened out that area is going to be. And we have, again, ending behavior for an odd function. The ending behavior is going to be opposite directions. So you need to put down here in red, ending behavior for an odd function is going to be opposite directions. Opposite directions. Now, what else do we have? Well, we have the f of x is equal to absolute value. This one's easy to remember because you have absolute value and then you have absolute vodka. Value and vodka start with a V. And that's what the absolute value is going to look like. You also have f of x is equal to the square root of x. The square root is going to look like this. You also have f of x is equal to 1 over x. 1 over x looks like a half a volcano. F of x is equal to 1 over x squared, which looks like a full volcano. Now, and you need to save the other for logarithm. We'll put a logarithm up later, and 2 to the x, so we'll put them up later. Okay, we're not going to do those right now. But you should have a firm grasp of all of these functions. These are called the parent functions, or the parent graphs. It's very important that you write those down, and I would highly suggest that you do the logarithm, put on the back on this one, if you make a space, f of x equals log of x, and f of x is equal to 2 to the x, and that's pretty much it. Okay? Now, what do you do with these? Well, what you do is, and I'm going to put these, I'm going to put these in, well, just let me write it down. I'll do it in blue, because now you're going to put down in each one of them what these are going to look like. So, f of x, let me erase that linear. You don't have to, you just put it wherever you want to. F of x is equal to a times x plus h plus k. See, this is to the first power. This is going to look like f of x is equal to a times x plus h squared plus k. This is going to look like f of x is equal to a times x plus h to the even power plus k, and so on. F of x is equal to a times x plus h to the third power plus k, and that would be to the odd power. This is going to look like f of x is equal to a absolute value of x plus h plus k. This is going to look like f of x is equal to a times the square root of x plus h plus k. This is going to look like f of x is equal to, you can see it a couple of different ways, but I'm just going to make it simple, 1 over a times x plus h, oops, I messed that up, x plus h plus k. F of x is equal to 1 over a times x plus h, quantity squared, plus k. And you'll see the other two written as a f of x is equal to a log of x plus h plus k. And f of x is equal to a times 2 to the x plus h plus k. Now, all of these are in the standard form. Now, I'm going to go to the next page, and we're going to talk about what the A stands for, what the H stands for, and what the K stands for. Okay, so the next page, we're going to talk about that. Okay, so with that being said, next page, please. What does the A stand for? Well, the A is orientation. The A basically means, what does the graph look like? We know what the model is. We know it might be a parabola or a straight line or a squiggle or a V. We know what the graphs look like because we got the previous page. We got the parent graphs. But is it compressed? Is it stretched? Is it going in the upward direction? Is it going in the downward direction? That's what the A tells us. And we'll get to that in just a minute. The H is the horizontal shift. I don't think I spelled that right. That don't look right. Maybe this, there. Horizontal shift. Now the only thing that you have to remember with the H is negative means to the right and positive means to the left. Do you remember us doing the vertex and the completing the square? And when we did the vertex, we took the opposite. That's why. When you're dealing with the vertex, you take the opposite of the number. And that's where that comes from. The vertical shift is K. Now, since it is in the intercept form, which is y is equal to a times x plus h plus k, do you remember us writing it in the intercept form? And you just bring this down, okay? And that's going to be your x of your vertex and your k. You just bring it down. Now, when we had it in a different form, we took the opposite of that. And with that, we explained that in the previous, when we did completing the square. So orientation is the A. The horizontal shift is going to be the opposite number, K, or H. And then the vertical shift is basically you're going to move it up and down. Now, what in the world does all this mean? Well, let's take, for instance, y is equal, or f of x is equal to x squared plus, or just x squared. Okay, I'm going to bring in my handy-dandy graph paper. I'm going to bring in my handy-dandy graph paper, and we're going to make a big graph. And I would suggest that you make your whole piece of paper, maybe turn it landscape, and make this your graph. And I'm going to put a big x-axis and a big y-axis. Here's my x-axis, Make sure you try to draw it as straight as you can. And here's my y-axis. Well, that wasn't worth a flip. Let's make the y-axis start. Okay, it's not going to cooperate, so I'm going to have to move it. Okay, there's my y-axis. And of course, it didn't. Okay, that's good enough for government work right now. It's close enough to see. Now, I'm going to draw f of x is equal to x squared. And I'm going to do it in black because x squared is the parent graph. Look on your parent graph, and you've got x squared. That's a basic model. So we're going to go with the basic color car, black car. Black car is basic. So x squared. And we use our method 1 graphing, -2, -1, 0, 1, and 2. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And I'm going to graph that in black. So -2, +4. -1, +1. 0, 0, 1, 1, and 2, 4. I'm going to go ahead and do 3, 9, 4, 5, 6, 7, 8, 9. Just so everybody can see where this is going. And there is your parent graph. That is the parent graph that's on your sheet of paper that says f of x is equal to x squared. Everybody with me? Now, I'm going to do in blue, I'm going to do f of x is equal to 1/2 x squared. So I draw my, and since it is a fraction, and if you watch my graphing my graphing video, I always use multiples of the denominator, so I'm going to do -4, -2, 0, 2, and 4. -4 squared is 16. 16 divided by 2 is 8. -2 squared is 4. 4 divided by 2 is 2. And 0, 2, and 8. And now I'm going to plot this in blue. So -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. -2, 1, 2, 0, 0, 2, 2, and 4, 8. Okay, somebody tell me what happened. Oops, that didn't go well. What happened to my blue graph compared to my black graph? It's wider. So I'm going to put wider down here. And I'm going to put that it's stretched along the x-axis. And it's what? What happens? What would you have to do to your y-axis to get it to spread out? You'd have to compress along the y-axis. Compress on the y-axis. Think of a balloon. If I compressed a balloon down and up, it would spread out. If I stretched a balloon from the sides, it would spread out. So when A is between 0 and 1, meaning a fraction, a proper fraction, it's going to compress along the x-axis and stretch along the what? Along the x-axis. It's going to compress along the y-axis, and it's going to stretch along the x-axis, and it's going to make it wider. So you can write down if A, and this is not only true for parabolas, it's true for every single one of your family graphs. If A is between 0 and 1, it's going to make your function wider, meaning that it's going to compress along the y-axis and it's going to stretch along the x-axis. Well, what happens when it's above 1? Well, let's go down here and let's do f of x, and I don't use red, but We'll use it this time, 2x squared. In this case, a is greater than 1. What happens when a is greater than 1? Well, let's do our handy dandy. -2, -1, 0, 1, and 2. -2 squared is 4. 4, 2 is 8. -1 squared is 1. 1 times 2 is 2. 0, 2, and 8. So -2, positive 8. -2, positive 8. 0, -1, positive 2. 0, 0, 2, and 8. What happened here? Well, now we are stretching along the y-axis and we are compressing along the what? Along the x-axis. So when a is greater than 1, we make it's more narrow, and the reason it's narrow is because we stretch on the y-axis and we compress on the what? On the x-axis. Think of a balloon, and you've got your hand on the left side of the balloon and the right side of the balloon, and you push your hands together. The balloon is going to elongate. If you take the balloon from the top and the bottom and you pull up and down, it's going to elongate. So when you have a narrow, when you have a number in front of your x value and it is more than 1, then that means you're going to have a more narrow version of your parent graph. What else can you do? Well, what about this one? Let's use for day. F of x is equal to -2x squared. -2, -1, 0, 1, and 2. Now I'm going to take -2, I'm going to square it, I'm going to get 4. 4 times -2 is -8. -1, that's going to be -2. 0, -2, -8. So now I got -2 to 8. -1 to 2. 0, 0, 2, and 8. Now somebody tell me what you notice about the green one. The green one is exactly like the red one, only it's in the opposite what? Direction. So, if A is negative, it's concave down. If A is positive, it's concave up. So now we have found out that A not only tells us if it's going to be compressed or stretched, but A is also going to tell us if it's concave down or if it's concave up. Which positive and negative in math and science tells us what? It tells us direction. So if you have a -2, that 2, you know what the 2 means. The 2 means it's going to be narrow like the red. Only the negative means that you take the red and you flip it over and it becomes green. So that's what A tells us. A tells us orientation. And what does A tell us with orientation? It tells us whether it's compressed, whether it's stretched, or whether it is, not stretched, whether it is wide, meaning that it's compressed along the y-axis and stretched along the x-axis, or it's narrow, which means it's stretched along the y-axis and compressed along the x-axis. That's what A tells us. So what does H and K tell us? Well, let's erase this. Let's erase most of this. Let's erase this one. We're going to leave our graphs on there. And hopefully you've got some room on your graph paper to write a couple more. We're going to take all of these off. And I'm going to come back with some different colors. Oh, shit. I'm going to have to re-put my line on there. Sorry. I'll just start it from right there. No, I don't want to do that either. Oh my goodness. You'll have to forgive me. I've done about 4 of these videos today, so I'm about tired. Okay, let me draw one the other direction. Okay, so what if we have, and we'll do this in burnt orange, what if we have this? F of x is equal to, let's go with positive 2, x plus h, quantity, I'm sorry. we're going to have to do something different here. We're going to have to erase this. Yeah, I can do that. Yeah, we can do that. Sorry, I'm talking to myself. F of x is equal to 2 times x plus 2, quantity squared, minus 3. Okay, so let's do our negative 2, x and y, negative 2, negative 1, 0, 1, 2. So, negative 2 plus 2 is 0. 0 times that'll be negative 3. Negative 1 plus 2 is 1. 1 times 2 is 2, minus 3 is negative 1. 0 plus 2 is 2. 2 squared is 4. 4 times 2 is 8. 8 minus 3 is 5. 1 plus 2 is 3. 3 squared is 9. 9 times 2 is 18. 18 minus 3 is 15. 2 plus 2 is 4. 4 squared is 16. 32. 32 minus 3 is 29, I think. I'm going to need to go the other way. Let me do a negative 3 right here. Negative 3 plus 2 is negative 1. Squared is 1. 1 times 2 is 2. 2 minus 3 is negative 1. All right, let's plot those points. Negative 3, 1, 2, 3, negative 1. Negative 1, negative 1. Negative 1, negative 1. 0, negative 5, or 0 and 5. 0, 1, 2, 3, 4, 5. And 1 and 15. Oh, wait, 1 and 15, that's 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. All right, that's how we're going to go there. And we got to plug in, we didn't plug in, we did, let's say 2, 3. Let me put in a 3 right here. Negative 2 is negative 3. I don't know why I didn't plug that one in. I'm sorry, down here. Anyway, plug in all the points, if I ever get there. Negative 2, negative 3, 1, 2, 3. There we go. And I need a 4. 4 plus 2 is 6. 6 squared is, good gracious. No, negative 4. No, negative 4. Negative 4 plus 2 is negative 2 squared is 4. 8 minus 3 is 5. So 4 is going to be 5. Now, I want y'all to look at this. And I'm going to go ahead and put this one over here too. Right here, I believe. And watch what happens. It's the same function as the red function, except we have a horizontal shift of 2 to the left and 2 down. 2 to the left and 2 down. 2 to the left and 3 down. So this is your horizontal shift. And remember, it's always the opposite. And this is your vertical shift. So your vertex is -2 and -3. And this can be done with a lot of your quadratics. Now, I'm going to tie it in with completing the square because some of you may be a little bit confused on how to get it that way. Oh, hold on. Let's see if I can do this. I was wanting to get rid of that, but I'm not going to. Look here. F of x is equal to x squared minus x plus or minus 8. I think we did one like this. Now at this point, you have no idea what this function is doing. You know it's a parabola, and you know it's opening up to this concave up because this A is +1. So you know that. You know it's got a y-intercept of -8, but that's all you know. So how do you change it? You do completing the square. X squared minus x plus blank is equal to 8 plus blank. I went ahead and set it equal to 0 and then brought the 8 over. Half of 1 is 1/2. 1/2 squared is 1/4. X minus 1/2 quantity squared is equal to, this is 2/4, I mean, this is 16, 32 fourths, 33 fourths, and now you've got the horizontal, that's 1/2, and -33 fourths. That is our vertex. And remember, your vertex is the opposite of both. Now, if I wanted to write it down and do the vertex form, I'd get f of x is equal to x minus 1/2 quantity squared, and then I would bring that -33 fourths over, and that's, remember me telling you that that's the form they like it written in? That would be this form right here, like that. And now, see what completing the square gives you, and now you can finish it by solving, and you'd solve it, take the square root of both sides, you'd get x minus 1/2 is equal to the square root of 33 over 2, and then x is equal to the square root of 33 plus 1 over 2, and then of course you could graph the function. Now what I'm doing here is I'm tying in the last video of completing the square to what I'm showing you now with the horizontal and vertical shifts. So do you use completing the square to find out where all the horizontal and vertical shifts is? Yes. You use completing the square to find the vertex and the x-intercepts. You have the y-intercept, and you take those 4 points, 1, 2, 3, 4, you take those 4 points and you sketch your graph. Or you could be given this on a test or a homework problem, and they ask you to sketch this graph, and you go, okay, that means it's opening upward and it's going to be skinny. We know that this is the horizontal and the vertical shift, so my vertex is right here. And then you could solve it, finish solving it, and you could bring a 3 over and solve for x and get the x-intercepts. So all this ties in together with the parent graphs, and with the parent graphs, you should be able to complete the square and do the vertical and horizontal shifts, or you should be able to look at a formula or a function and be able to move left and right and be able to tell if it's compressed or stretched along the x and y axis. And that's called the parent graphs.